Welcome back to another explainer. You know those heavy little black boxes you plug into the wall to charge your phone or your laptop? We use them literally every single day, right? You just plug them in and boom, magic happens. But have you ever stopped to wonder what is actually going on inside those things?
Well, picture the fundamental dilemma we're dealing with here. The power grid delivers electricity to your wall outlet as alternating current, or AC. And depending on where you live, that's often a massive, honestly pretty dangerous 230 volts of wild energy, oscillating back and forth 50 times every single second. Now think about your delicate smartphone or your laptop. If you hit them with that, no way. They would be instantly fried. They absolutely require a calm, steady, unwavering stream of direct current, or DC, just to survive and function. So how do we bridge that gap? How do we take that wild, oscillating wave and actually tame it?
Okay, so to tame that wave, we're going to follow the electrical current through a four-stage assembly line: transformation, rectification, filtering, and finally, voltage regulation.
Let's dive right into stage one, transformation.
Before we can even think about changing the type of current, we have to deal with its sheer, overwhelming size. Our journey starts at a step-down transformer. This device basically takes that primary AC voltage coming from the wall, let's say 230 volts, and reduces it to a much lower, way more manageable secondary voltage. It does this by using two coils of wire. If the transformer has a turns ratio of, say, 10:1 between the primary and secondary winding, that intimidating 230 volts gets stepped down to a much safer 23 volts. It's the exact same oscillating wave, just shrunk down to a size our electronics can actually start to handle. And that is the very first, absolutely crucial step in protecting our devices.
Moving right along to stage 2, rectification.
So our wave is definitely smaller now, but it's still oscillating back and forth. We really need to force this current into a one-way street. We do this using diodes, which essentially act like one-way valves for electricity. Now, a half-wave rectifier uses just one diode. It lets the positive half of the wave through, but entirely blocks the negative half. The problem? That leaves these huge gaps of zero voltage. It's incredibly wasteful. But by cleverly arranging 4 diodes into what's called a full-wave bridge rectifier, we don't just block that negative half, we actively flip it positive. So now we're capturing everything, creating this continuous series of pulsating bumps.
And what you really need to take away here is the massive difference in performance. A halfway rectifier, it only manages a maximum efficiency of 40.6%. Think about that. Nearly 60% of your power is just gone, totally lost. But the bridge rectifier, even though you have to use 4 diodes, hits a massive 81.2% efficiency. This huge leap in performance is exactly why almost all modern electronic power supplies use the bridge rectifier method. It's a total game changer for converting AC power into DC power without just throwing away massive amounts of energy.
Which brings us to stage 3, filtering.
Okay, even though our current is finally moving in just one direction, it's still a really bumpy, pulsating wave. If you fed that straight into your speakers, you'd get this terrible humming noise. So we have to smooth it out. The main enemy we're fighting here is called the ripple factor. Basically, that's just a measure of the unwanted, fluctuating AC component that somehow sneaks through the rectification stage. For true high-quality DC power, we need that ripple factor to be as close to 0 as physically possible.
To defeat that ripple, we use a filter, and most commonly, that's going to be a capacitor. Honestly, the best way to think about a capacitor is kind of like a tiny water tower. When the pulsating voltage peaks, it fills up the water tower, meaning the capacitor charges. But then, when the voltage wave dips back down, the capacitor steps right in and smoothly discharges its stored energy into the circuit, essentially filling in those gaps. It chops the peaks, fills the valleys, and turns those harsh, deep bumps into a much, much gentler, shallow ripple.
And that leads us to our final boss, stage 4, voltage regulation.
All right, so we've stepped down the voltage, we've forced it into one direction, and we smoothed out the worst of the bumps. But an unregulated voltage is still slightly wavy. And even worse, it can actually fluctuate if the input voltage from your wall changes or if your device suddenly demands more power. We have to transition from that kind of shaky, unreliable input to a pristine, perfectly constant, regulated voltage. This perfectly flat line is exactly what your sensitive microchips absolutely demand to function.
So how do we get that perfect flat line? Well, we use a fascinating little component called a Zener diode. Now, normal diodes usually get destroyed if you try to push current backward through them, but a Zener diode is uniquely designed to operate in what's called a reverse breakdown region. Basically, once it hits a very specific voltage, known as the Zener breakdown voltage, the current just drops straight down.
This means it can allow varying amounts of current to pass through it while stubbornly holding the voltage across it exactly in place. It acts like this unyielding guard at the end of the line, trimming off the last few remaining ripples.
In a lot of modern electronics today, engineers actually package this entire regulation stage into a single, compact integrated circuit, or IC. Take the really popular 78XX series, for example. A chip like the 7805 takes that slightly wavy, filtered DC input and effortlessly outputs a rock-solid fixed 5 volts. And it gets better. These tiny chips have built-in internal thermal overload protection and short-circuit limiting, so they don't just provide that perfect flat line, they actively protect the entire system from completely self-destructing if something happens to go wrong.
So mapping out this entire electrical journey is kind of like looking at a treasure map. We start on the far left with the wild high-voltage AC from the wall. Step 1, the transformer shrinks it down. Step 2, the diode rectifier flips those negative waves, creating pulsating DC. Step 3, our filter capacitor steps in to fill the gaps and smooth the wave. And finally, Step 4, the voltage regulator locks everything down into a perfectly flat, safe, steady DC output for your device.
It really is a marvel of everyday engineering, isn't it? Without this invisible, miraculous 4-step assembly line silently working away inside every single charger and power supply you own, the digital age literally could not exist. Our laptops, our smartphones, the very servers hosting the internet, they all completely rely on this process. So the next time you plug a device into the wall, maybe take just a second to appreciate the intricate little journey happening right there in the palm of your hand. Because honestly, you have to wonder, what would our modern digital world even look like today if we had never figured out how to tame that wild wave? Thanks for joining me on this explainer, and keep your curiosity focused.